Section 5.2 is about large prime numbers. And the reason why large prime numbers are of interest is because encryption, which of course is a hot topic nowadays for data encryption, cell phone transmissions, and so on, that's a very, very important topic, that things can be kept away from those who are not supposed to see it, which of course has been a problem for thousands of years also, when messages got intercepted and there's plans for attack on armies and all of that. So people came up with encryption methods a long time ago. But in our technological environment today, large prime numbers play a very important role in that. So the objectives here in section 5.2 is to prove the infinitude of primes, which means infinitely many, and then identify prime numbers of several categories, and then we explore several potential prime number generating formulas. Okay, so there's a proof that there are infinitely many prime numbers. And to better understand that, let's look at the following argument. Let's say we have a number m equals 2 times 3 times 5 times 7 plus 1 equals 211. Now notice that m is a product of the first four prime numbers, 2, 3, 5, and 7, plus 1. So if we divide 211 by each of the prime numbers, 2, 3, 5, and 7, the remainder is always 1. So that is the key thing. If we divide that number, m, by each of the primes, the remainder will always be 1. So, and here's how you can see it. So we divide 211 by 2, 105. 105, rather, there would be a remainder of 1, similarly divided by 3, the remainder is 1, etc. The remainder is always 1. So that's a key observation. And that's important to understand for the proof that's coming up next. So in other words, 211 is not divisible by any of the primes 2, 3, 5, and 7. And now we can present Euclid's proof that there are infinitely many primes. If there is no largest prime number, there must be infinitely many primes. So here is how we prove the infinitude of primes. And that's a proof by contradiction. You may not have never seen this before, but here's the way it works. Number one, we assume there is a largest prime number called p. So we form the number m such that m is equal to p sub 1 times p sub 2 times p sub 3 times p plus 1. So where p is the largest prime number. So in other words, p sub 1, p sub 2, etc. up to p represent all the prime numbers less than or equal to p. Now m must either be prime or composite. That's the only choice. Now, here's how it begins. Case number one, we suppose that m is prime. M is obviously larger than p, because we have factors plus we add 1 to it. So if m is prime, it is larger than the assumed largest prime. So in other words, we have reached a contradiction. In other words, oh, I'm sorry, I covered that up. Let me just move it up a little bit so we can see it. Okay, so the first assumption is that m is prime. The number we just formed here as a product of prime numbers less than p and up to p, including p. And then m is either prime or it's composite. So if we assume that m is prime, obviously m is larger than p. So if m is prime, it's larger than the assumed largest prime p. So we've reached a contradiction. Now, in the case number 2, we suppose that m is composite. If m is composite, it must have a prime factor, but none of p1 sub t, p sub 2, p sub 3, etc. is a factor of m, because each division by each, or each because division by each will leave a remainder of 1, if we look at the previous example. So, if m has a prime factor, it must be greater than p. But that's a contradiction, because p is assumed the largest prime. So we have a contradiction either way, and so that means the whole argument was based on the assumption that there is a largest prime, but this leads to a contradiction. So there must be no largest prime, or put the other way, there are infinitely many primes. You may go over this a couple of times to get your head around it, but it's a very elegant proof. And remember too that this proof was developed thousands of years ago. Since we cannot really investigate all infinitely many primes directly, people have broken down the set of natural numbers into smaller sets, the familiar ones, and try to generally either disprove the property or prove it through deductive arguments. And so one way to partition the natural numbers, in other words, divide them into disjoint subsets, whose union is the entire set, goes as follows. So let's say set A is all natural numbers of the form 4k. And then set B is a set of all natural numbers of the form 4k plus 1. And C is a set of all natural numbers of the form 4k plus 2. And then lastly, D is a set of all natural numbers of the form 4k plus 3. And to see what this looks like, let's do some of the partitioning of natural numbers. And so here's the procedure. So set A is of the form 4k, set B is 4k plus 1, set C is 4k plus 2, and set D is 4k plus 3. So in each case, k is a whole number. So here we are asked to list the first 8 members of the infinite sets A, B, C, and D. So we're going to do that. So set A is obviously all the multiples of 4. So set A is equal to 4, 8, 12, 16, 20, 24, 28, 32, and the pattern continues. And then B would be the set equal to 1 when k is 0. So 1 and 5 and 9, 13, 17, 17, 21, 25, and 29, etc. And then C would be, 4k plus 2, so it begins as 2, 6, 10, 14, 18, 22, 26, 30, etc. And then D would be 4k plus 3, so it begins with 3, 7, 11, 15, etc. 19, 23, 27, 31. And the pattern continues. So next we're going to talk about Mersenne numbers and Mersenne primes. And probably in the beginning, more out of curiosity than anything else, it's hard for me to imagine that Mersenne primes, Mersenne numbers were of great interest at that time. Mr. Mersenne was a priest and a monk rather, and he lives 1588 to 1648. So anyway, but he is famous for developing large prime numbers. So for n equals 1, 2, 3, etc., the Mersenne numbers are those generated by this formula. M sub n equals 2 to the n minus 1. So n equals 1, 2, 3, and so on. So it would be 2 to the 1 minus 1, or 1, or 2 to the second power minus 1 would be 3, etc. So here's the observations. If n is composite, then m sub n is also composite. If n is prime, then m sub n may either be prime or composite. So in other words, if n is composite, then the result will be composite. But if n is prime, then m sub n could be prime or could be composite. So then we want to look at that and see what can we prove about these things being prime numbers. So the prime values of m sub n are called Mersenne primes. Large primes being verified currently are typically Mersenne primes. Again, they're of great demand, these large prime numbers, for encryption purposes. And there may be some other reasons too, but certainly for encryption purposes. In example 5, we are asked to find Mersenne numbers for n equals 2, 3, and 5. So then m sub 2 equals 2 to the second power minus 1, which is 4 minus 1, and that's equal to 3. And m sub 3 would be 2 to the third power minus 1, and it would be 8 minus 1, and that's equal to 7. And m sub 5 is equal to 2 to the fifth power minus 1, which is 32, minus 1, which is equal to 31. And so these are, of course, all prime numbers, 3, 7, 31, all prime numbers. It's interesting to note that if you compute, for example, m sub 11, the 11th Mersenne number, would be 2 to the 11th minus 1, which would be equal to 2047. Of course, 11 is a prime number, but 2047 is not a prime number. That's equal to 23 times 49, 89 rather. So it's not necessarily true that when you have a prime number for n, that you get a prime Mersenne number. 23 times 89. Yeah. Pierre Fermat was a very famous French mathematician in the 1600s, and he conjectured that the formula 2 to the 2 to the n minus 1 would always produce prime numbers. And so when we look at that, when we look at the numbers that are generated by this formula, when n is equal to 0, then 2 to the n to the 2n for n equals 0 gives us the number, the number plus, oh I'm sorry, that should be plus 1. It gives us a prime number of 3, and for n equals 1, it's certainly true that 4 plus 1 is 5, and then for n equals 2, that'll give us 2 to the n gives us 16, and 16 plus 1 is 17, and so on. Then when n is equal to 3, 256 plus 1 is 257, so that gives us a prime number. So other people try to come up with formulas to generate prime numbers, and a very famous mathematician, Euler, depending how you pronounce it, it's actually pronounced Euler, but most people pronounce it Euler. So he came up with a polynomial n squared minus n plus 41, and so for up to n equals 5, you do have prime numbers. And the same for Ascot. Ascot came up with this polynomial, n squared minus 79n plus 1601. And so for n equals 1, we have these in the following prime numbers. But all of these formulas fail at one point or another. So in example number 7, we look at confirming the failure of Euler's and Ascot's formulas. So the A part says, show that Euler's formula works for some but not all values of n greater than 40. So when we choose n equals 41, the polynomial n squared minus n plus 41 gives us the number 1681, which is equal to 41 squared. So obviously it's a composite. So, and then when n equals 42, from the formula n squared minus n plus 41, that gives us 41 times 43. So obviously composite also. And then when n is equal to 43, the formula gives us the number 1847, which is prime. So in other words, Euler's formula works for some numbers, for n, but not for others, even when n is rather large, like over 40. So that's another point, that no one has ever really come up with a formula that consistently produces large prime numbers. Now, Ascot's formula was equal to n squared minus 79n plus 1,601. It's interesting to note that I don't think anybody knows how they came up with the formula, but apparently it works for a lot of numbers. But so when n is like equal to 80, which is greater than 79, so n equals to 80, the formula gives us the number 1,681, which again is equal to 41 squared, which is of course composite. And then for n equals 81, when we plug that into this formula, and the little formula for that, we come up with 1,763, which can be written as 41 times 43, similar to the Euler formula, which of course is also composite. And when n is equal to 82, then Escott's formula gives us the number 1,847. And as we had observed before, that is a prime number. So again, neither Escott's nor Euler's formula gives us reliable prime numbers for n greater than 40 or 79 respectively. Let's look at a little exercise here. For the composite number n equals 6, find m sub n, 2 to the n minus 1. So that means m sub 6 is equal to 2 to the 6 minus 1, which would be 64, minus 1, which is 63, which of course is composite. It is 9 times 7, so it's composite, as we would expect because n is composite. And then similarly find m sub n equals 2 to the n minus 1 for n equals 10. So m sub 10 is equal to 2 to the 10th minus 1, which is 1,024 minus 1, or 1,023. Which is composite also because it's equal to 3 times 341. Again, as you would expect, because n is composite. This then concludes section 5.2.